SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2 Module 12. We were doing process FMEA, and in context of it, which we had identified some failure modes and tried to actually do countermeasures so that these modes get eliminated. So we did the first mode, which was about inserting or adding a positive depth stop layer with a limit switch which would actually do the dispensing of the spray. Okay. And there we found out that there is a reduction in the risk priority number from 280 to 70. The other is basically the spray heads clogged. Here the spray heads clogged problem, which is the number 2 problem, okay, which was having a RPN of 105, was really about that the viscosity was too high or temperature was too low or the pressure was too low. So there was no as such set pattern as to what would be the ideal temperature, viscosity and pressure at which the wax flow could happen in an uninterrupted manner, and then it could prevent the prevent the clogging of the nozzles or the sort of hindrances to the nozzle, etc. So here the assembly engineering decided, or the process engineer decided, to use a DOE or a design of experiments scheme where you could optimize the various parameters related to the temperature, viscosity and pressure, and there was an optimization carried out based on viscosity versus temperature versus pressure here, and some solution was provided as to what would be the ideal ranges of these different values. Okay. And so manufacturing engineering again was given a target of implementing this by a certain date, which they did. So the temperature and pressure limits were determined and limit controls now were installed. For example, there would be a thermocouple inserted inside the bottle of the wax, which would be fed into the pumps, so that the moment the temperature goes above a certain limit, the pumping would start. So there is some kind of a foolproofing switching which has been established between the bottle of the wax fed into the system and the pumping unit. Okay, so it can be set at the particular temperature range in question, and then also some controls have been inserted on the pressure at which the dispensing can happen. So there is a pressure gauge which is going to give you the operating pressure of the liquid wax or the molted wax within the circuit, and that is also going to in a way control the spraying process. So unless and until the pressure is attained, or unless and until a certain set value of temperature which has been arrived at from the DOE design of experiments have been attained, the wax will not even flow into the system. So obviously after that the control charts, which I will talk about in details following this particular module, they were plotted, and a CPK value was of 1.85 was shown in the process, and I will actually in detail illustrate how control charts can be plotted and calculate CPK for you later modules. But then this was a very good optimization experiment suggested by the assembly engineer, and the manufacturing engineering implemented it. Now let's look at what is the RPN because of the implementation of the same. So obviously the severity and the detectability doesn't change, because the process of checking is still the spray pattern test which was there earlier, or maybe even preventive maintenance schedules which were earlier for preventing this problem. But then the occurrence has reduced really from 30% value earlier, 50% value earlier, as you can see here, all the way to about 10%. Okay, so the occurrence of this defect has reduced because of the countermeasure, and subsequently the RPM has come down from 105 as shown in this particular column 17, column 18 to 21. Okay. So in the first problem which was identified, the RPN was reduced from 280 to 70, and the second problem it comes from 105 to 21. So both the countermeasures which have been implemented show efficacy, and they show that there is a reduction in the occurrence because of those countermeasures, and this way a correct documentation of the process plan has been prepared, and now you have to follow the standards which have been obtained, or the checkpoints which have been obtained at the various levels, like the automation foolproofing, or even the DOE based analysis of the temperature pressure ranges, and then also control limit switches which would ensure that this would happen. Okay, and so always there would be a low occurrence based on such a complete illustration. So essentially FMEA is nothing but an organized approach of problem solving by identifying what are the many causes which are there and trying to eliminate with countermeasures some of the causes which are the most occurring ones. Okay, so that is essentially what FMEA is and nothing beyond. Okay. So we leave the spray head deformed problem due to impact because of the low RPN it already has. So it is not really of critical importance to us at this particular level, it is 28 RPN. The other which is very important is spray time insufficient, because as you know the RPN was very high of 392 earlier, and we would like to reduce this. So basically here the whole process engineers who were there suggested that you install a spray timer. So unless and until this whole time cycle of spraying of the wax is proceeded, there is no way that the dispensing can stop. Okay. So therefore the operator has to actually now not only rotate the nozzle handle in the complex profile that has been shown in the door lower all the way, but it has to be smoothened up with the total timing of the spray, so that obviously if at one place the spray is more and another is less, there would be a beading in the place where the spray is more. Okay. And that can be detected in the subsequent stages when they are going to check for the critical coverage of the doors by looking at 10 doors per shift and lot sampling. So they are also going to investigate what is the depth of the wax lining which has been laid in, and any beading or any area which is insufficiently covered would come up in such a checkpoints. So therefore this spray timer was a very important aspect which was inserted in the system, that unless and until the wax is completely covered, or unless and until the total time that the wax is supposed to be covered for executes, the dispensing will not stop. Okay. So therefore the operator has to keep the gun inside the door for that particular time and nothing beyond. So obviously when the operator knows that it has to, because otherwise if he just pulls out the gun, the dispensing will still be continuing and it will spread on the different members of the car body, like the, let us say, the door inner, or even to some extent the station that he is standing, etc., and he will avoid this unpleasantness. So it is a foolproofing on the timing that he is spending to doing the wax spraying. That is number one. Number two is that obviously because of the correct lot sampling in terms of the depth of wax, etc., and the measurements therein, if he even dispenses it for the same amount of time duration but only at one place within the door, that is also going to get caught up. Okay. So it is some kind of a foolproofing. So here the maintenance engineering was given this initiative to install the spray timer. Obviously it was in the machine that this timing was given, because from one cycle to another the PLC or the programmable logic controller in the machine would have to be given a timing clause, okay, so that the cycle does not end before the timing ends. Okay. And this automatic spray timer was installed by the certain target date which was given, and the operator starts the spray and timer controls shut off. So then a control chart was processed or plotted again, and it was showing a CPK value of 2.05, which is reasonably good. Okay. And so therefore what was observed again in the terms of occurrence, that the 80% occurrence which was happening earlier because of this one step was about 10% now, and the RPN obviously reduced because of that to 49 from 392. So in a way what you have done is you have identified the three top causes and you have taken countermeasures to the three top causes, and with the RPN sequence you are trying to see if the RPN is getting reduced. So is there complete effectivity or efficacy of the control that has been introduced, okay, or the new process modification that has been introduced, which will not allow the particular reason or the cause of the failure to happen, so that the overall failure goes down because of that. So that's, it's also known as a defect tree analysis sometimes. That is how FMEA process works. You are probably now quite aware of how FMEA can be carried out. And so now we will just go to the next section, which is sort of important here, which talks about how to improve product quality during the production phase. So obviously quality can be designed into a product, as you have seen earlier through Taguchi's robust design approach, and then the product needs to be manufactured, and so therefore the control of the quality of the product during the manufacturing process is also very, very essential. So there may be some assignable causes which may occur, and they may seemingly be random at beginning, but then there is a set pattern of these causes which would go over a long time duration, which would lead to the change in the manufacturability, manufacturing quality of the product, etc. And these assignable causes, if allowed to continue for a long time, may eventually lead to the shift of the process to be out of bounds, okay, of the limits which the process is designed for, and there has to be some kind of a counteraction which is taken at that level so that it comes back to normalcy, and within the control guidelines which have been given for the process, the product flows, okay. And so therefore it is very, very important to reduce what you call the variability of a production process, so that the output quality is always going to be good quality, okay. And then it can obviously eliminate costs, it can eliminate wastes because of this complete, you know, control of the manufacturing process. So you saw earlier with the FMEA analysis how we have solved a problem in the manufacturing process. Now there are many other ways and means for solving, you know, or for maybe coming to a reverse gear a little bit and trying to look at whether the process is a controlled one, or if it's out of control, then can we bring it back to control. So there are many real-time strategies which are involved, and one of them is obviously control charts, where you can actually see a measurable dimension of, or an output or a quality characteristic coming out, and you can monitor that with some control guidelines which are actually the upper and the maximum upper and the maximum lower limit of the particular parameter that is allowed in the system, and the moment it goes outside that, you start focusing on the process and control the process so that it can come between that control guidelines. So in a way, if you look at it schematically, we have a transformation process as a manufacturing process, many inputs like material, machine operator, information, others on this transformation process. Obviously it gives an output, okay, and then there are certain sampled outputs which are measured, and there are detectable assignable causes which are made, because of which whatever variation in the output is recorded is sort of identified, and then obviously the root causes have to be eliminated, and then again whatever implementing has to be done regarding the correcting measures which identify the root causes and eliminate them has to be fed back into the transformation process, so that it now has a measured output which is within reasonable limits, okay. So that's how the whole process of quality improvement can happen within any manufacturing process. It's very important, and there are many parameters which are, or there are many methods of study in which you can actually measure this output and report this output so that it can give you some kind of an understanding. So there are mainly 7 different tools which are used, and I can say that this use is more how to represent statistically the measured output in a manner so that it comes quickly to the eyes of the control management of the particular process, okay. So these are known as the 7 tools of quality control, and they are widely used as process improvement tools. So one of them is obviously the histogram, then we have the check sheet, the Pareto chart, the cause and effect diagram, the defect concentration diagram, scatter diagram, and finally the control charts, okay. So I'm going to now illustrate briefly about how these 7 tools of quality control can be utilized, or what they are really, and with a lot of emphasis onto this the last category, which is the control chart category, because this is something that is a real time health monitoring of a certain process, okay. So it's a parametric for illustrating that, and it has to be necessarily done within any transformation process to keep it in limits and bounds of whatever it has been planned for. So therefore let's look at the first aspect, which is the histogram. So obviously histogram is about laying out the measurements in terms of the measurement and the frequency. Let's say we are talking about a shaft, okay, and a machine produces a shaft within the tolerance limit of 0.995 inches and 0.95 inches and 1.05 inches, okay, and this is a numerically controlled machine that we are trying to measure the process capability of, and we are plotting the shaft diameters against the frequency for a sample of maybe let's say about close to 300 or 400 pieces, And here we see that out of the measurements of 300 and 400 samples out of maybe 30,000 which are produced by this numerically controlled shaft for a period of, let's say, 2 days or 1.5 days, you have a distribution in terms of a frequency, that means the number of occurrences with the shaft diameter. So on the x axis here you are plotting the shaft diameter. Let's say we are talking about a 1 inch diameter emanating from the process, and in this whole 300 measurements, 300 plus measurements, which are merely a sample representing the 30,000 pieces which are being made, you find out that the shaft of diameter 1 inches occurs something like 130 times. Okay. So this is the frequency, and you are plotting this histogram based on that diameter and the frequency over which that diameter is repeated. Similarly, you have measurements like 1.0, 1.99, etc., and their frequencies have been plotted in this particular histogram. So this is called a histogram, right. So this plot of frequency versus occurrence of the particular dimension, that means the dimension and the occurrence it has come, a number of occurrences that it has had, this is basically the histogram. You can see that it is sort of a bell shaped distribution like this that it is representing, and there are many other inferences that can be drawn by looking at this figure particularly. Okay. But we see that the distribution of the shaft diameter is quite symmetric about the mean value, that is 1 inches. Okay. So this is something that is a learning experience for us, that the process is within control, that when the specification says 1 plus minus 0.05, the maximum number of occurrences that are having, that we are having out of all the observations, let's say 300 plus samples out of these 30,000 observations which you are talking about, they are having a highest number of occurrences along the mean, that is 1 inches. Okay. So this gives you a very good idea whether the process is in control or not at a glance by looking at some process or system like this. So we will probably close on this particular module in the interest of time, but the other tools of QC, like let's say the defect chart or the control charts or even the scatter diagrams, etc., we will take up in the subsequent modules. Thank you so much.